Hello, everyone. In this week, we are going to start to look at the introduction to data visualization and the visual perception. So here's the table of contents for this module. First, we'll talk about what is data visualization. We'll give you a brief introduction to the history of data visualization. Then our focus will shift to visual perception and the building blocks of data visualization. Especially, we'll talk about the pre-attentive attributes, such as color, size, and other elements in data visualization that can help to facilitate the two thinking systems that we use to process the world around us. So first, let's talk a little bit about what is data visualization and why is it important. So take a look at this slide. So do you know what this is? So if you look at the comparison, we know it is a stained glass window. So it's actually the largest stained glass in the Western Hemisphere. So it's located in Covington, Kentucky, at the Cathedral Ballista. So this is actually what we're trying to do with the data, especially the purpose of data visualization. So what we're doing is just like the light to shine on this stained glass, to illuminate the stained glass, to make it vivid, to tell the story. So we will actually eliminate the data to help the audience to gain insights and then use our findings to make decisions. So essentially, we are trying to tell a good story based on the given data. So that's the purpose of data visualization and why it's getting so important. So visual analytics is a growing field. According to Gartner, the task of making hard types of analysis easy for an extended set of users will continue to dominate the business intelligence market requirements. Data visualization classes have been now taught at major universities. So here at UNF, we recently developed the BSM MSBA program, and the data visualization is one of the core courses required for the program. So many companies, they have already added visual analyst positions. So especially they're looking for storytellers to help companies to gain insights from the data being collected. For instance, at Facebook, at some leading hedge fund, and at Deloitte, we all see the openings related to data visualizations. So this person, Edward Deming, he said, "In God we trust, all others bring data." So Deming was the father of modern quality management. He was heavily involved in the economic reconstruction of post-World War II in Japan. So he was famous for his philosophy based on data quality, data management, data analysis. Essentially, he believes that if we have data, then we can actually develop superior performance in every aspect of business. So here is the process of business intelligence to guide us to move from data to action. So the idea is to use data, to collect data, and then to create information, then convert information to knowledge, eventually to develop plans to guide actions or key decisions. So you can see the difference between data, information, knowledge, and strategy, and how they evolve into the higher levels at different stages. So, but the data is the foundation, it's a raw resource for us to move into information, knowledge, and strategy. So here's one example. So if you look at this, it can be considered as a raw data set. So can you quickly find out how many times the digit 7 appear in this data set? I guess it's not so easy. You have to count. You have to move from each row to the other, try to find out and count the number of 7s. So what if we add a little color, some color, the blue color to the digit 7? Now it's a little bit easier. How about we make it bold and underlined? So you can see the differences, the changes we make to make it easy to find out the number of 7s. So the number of 7s we want to count is like the information. So if we make some changes, we can make it easier for us to detect the information, to summarize the information in the raw data set. So what we used is just some specific attributes like a color, size, orientation, texture that can help us to easily present the information to the audience. So these are called pre-attentive attributes, so which are commonly used in visual perception and data visualization. So like a length or width and position. So in addition, order is also important. So if we reorder the original data set, we can now see that there's exactly one row of data 7s on the first row. So we now have information about this data that we did not have before. So by changing the order, we can quickly turn data into information. So that's another very important pre-attentive attribute. So now we can actually even draw a bar chart to illustrate our original data set. So now we have more information about this data set. So in addition to the number of times the digit 7 appears, we now have additional information we can interpret. So we can also reorder the bar chart to make it easier to interpret. So compare the information we can obtain from the bar charts to these pie charts. So do you think is it easy to answer the questions as quickly and easily with these bar charts? So can we get the same information with the pie chart? So in order to move from data to information to knowledge to strategies, so we need to answer some questions like how many, how much, what are. And then we need to answer why questions and how questions in order to move down to the higher levels of knowledge and the strategies of wisdoms. Okay, now let's take a look at the brief history of data analytics or data visualization. So in the 2nd century, it was probably in Egypt. So that's where probably the data visualization was originated. So Claudius Ptolemy, so was the first, maybe considered the first person who used tables to tabulate data, to actually to illustrate something related to astronomy. So it was around 150 CE in Egypt. So it was considered probably the first step in shifting emphasis from text to perception, visual presentation. So it was the earliest preserved use of a table. So second one is Rene Descartes. He invented method of presenting number-based data using two-dimensional coordinate scales, which we now use in many of our scientific fields. So he was the person who had the famous quote, "I think there are n," and he introduced this Cartesian coordinate system. William Playfair was a Scottish engineer and a political economist. He was considered the founder of graphical methods of statistics. Especially, he developed new designs and improved the existing methods to provide systematic visual representations of his linear arithmetic. He created some very well-known charts, including time series line chart, bar chart, pie chart. Charles Maynard. Charles Maynard is also a well-known person in this field, in the field of data visualization, especially for his well-known map of Napoleon's Russian campaign. It was regarded as one of the best statistical graph ever drawn by some people. So we will discuss this map in detail in one of our future classes. Jacques Bertin was a French photographer and theorist. He was the author of many scientific maps, articles, and other papers on semiology. He studied science and how we can process visual information. John Tukey is an American statistician. He introduced the box plot around 1977. So box plot is also used widely nowadays in statistical analysis. So these are the visualization techniques commonly used in EDA, include box plot, histogram, Pareto chart, scatter plot. So these are all the advocacy of Tukey for EDA, for the analysis, exploratory data analysis. Edward Tusk is an American statistician, sculptor, and professor emeritus of political science statistics at Yale University. He is widely recognized for his contribution to information design and visual literacy. He is also considered as a pioneer in teaching the fundamental skills required for visual communication. His famous invention is called spark lines. So if you notice in the latest features of Excel, so you may see this kind of a type of charts called spark lines. It's a small scale line chart you can embed into a table or a spreadsheet, try to indicate the trends or maybe the future directions of certain data set. So that's called spark lines. William Cleveland is a professor of statistics in the computer science in Purdue University. He's another very important person in the field of data visualization. His early books are very fundamental and essential for the further development of this field. He is one of the first to study how people perceive information and which provides the building blocks for creating data visualization's best practices. So this is one of his major contributions, which is called Claudius chart. Especially, it's just the assembly of many kind of scatter plots together to provide insights of a large data set. Stephen Few is is one of the students of Edward Tusk. He is the leading author in the field of data visualization. He has written many successful books in the field of data visualization. So in addition to those important persons in this field, we also see other critical events that have facilitated the development of data visualization, especially due to the hardware pieces like this we have witnessed in computers, like the graphical user interface, mouse, and many other hardware pieces and equipment, which enabled us to create something we have never imagined before. Okay, so now let's take a look at the concept of visual perception. So in this week's discussion, I asked you to find an optical illusion image, and then talk about how like the color, size, or other elements are used in this optical illusion, and how this is related to data visualization. So this is important because it will help us to understand how our minds work and how we actually use our visual perception to understand data, especially the visual data being presented to us. So this will help us to guide our design in our future data visualization projects. So here are some examples you can take a look at. So to understand how actually different elements are used to actually deceive our eyes, to create these optical illusions. So essentially these are the same colors, the top and bottom. So here's another example. So for this data, what's the actual color? So one more example. So another example. How many colors do you see in this rectangle? So if we move the bar away, you are going to see there are 4 different colors. So here's another very famous example. The boy is standing in one side of the room and then on the other side of the room. It's the same boy in the same room, but what's happening here? Did the boy suddenly became like a taller, or what happened? So this is actually similar to what we normally do when we want to take a picture. Like when we go to Washington, D.C. at the monument, many people take these kind of pictures. So the Washington Monument is obviously not this small. It's simply because of the distance. It's far away in the distance, making it appear smaller. So that's a similar idea for this for the boy in the previous image. Let's take a look at this video.
Does what we see correspond to what's really out there? Or does our brain construct its own version of reality, one that does not always match up with the physical universe? Check me out, for example. I'm the same size here as I am over here, but over here, I look much larger. No, it's not a cheap video trick. It's a trick on your brain. Here's what you're seeing. The me over here is indeed projecting a smaller image onto your retina, the region of light detecting cells at the back of your eye. All else being equal, smaller images mean smaller things. Here, I'm in no danger of hitting my head on the ceiling. But over here, I am ducking. Ceilings are useful visual landmarks for judging size. Of course, you're making these size estimates based on the assumption that this room is ordinary and box-shaped. You assume the back wall is perpendicular to the line of sight. So the two versions of me are the same distance away. You're also assuming that the floor and ceiling are level and parallel. But as you probably guessed, this isn't the case. And the room isn't box-shaped at all. It's trapezoidal. The back left corner of the room is much farther away than the right. Since I'm farther away over here, my image is smaller, although I'm definitely not. The ceiling cue is also misleading. The floor actually slants upward and the ceiling downward from left to right, making my head much closer to the ceiling when I'm over here. Why couldn't you see these things and adjust your size estimates? The room's features have been cleverly distorted to be consistent with a rectangular shape. The checkerboard pattern on the floor gets finer grained toward the right, so that the same number of pattern elements fit in a shorter distance. The windows are resized and shaped to match the trapezoidal back wall. Your narrow angle of view from the front of the room blocks the cues that would reveal the room's true shape. And of course, we easily believe in a box shape because that's the shape rooms normally are. This clever setup is called the Ames Illusion. American ophthalmologist Adelbert Ames Jr. devised it in 1934 and built a physical example the following year. For Scientific American's Instant Egghead, I'm Ingrid Wickleven.
Okay, so this is called an Ames room. It's actually used in psychology for experiments to help people understand our visual perception. We are easily deceived by our eyes based on what we see in our environment. We tend to use our stereotypes and use some of the benchmarks to look at our surroundings to help us understand what's going on. So that's why many times we are easily being tricked. So here's another example of the railroad tracks. So the line in the distance appears to be longer than the one in front of us. But actually the lines are exactly the same size. So one more examples. So if we click all these dots, so we'll see the buttons. Some are stuck out, some stick out, others actually are pressed in. So our minds will expect light coming from above, putting the top of the buttons in light and bottom part in shadow. So if we rotate this slide, we're going to see the opposite effect. So this is a picture of a crater from Wikipedia. So if we turn around this slide, now you can see it's like we're climbing the hill. This is called the Moore effect. So do you notice the shimmering effect if you stare at the image? There's actually no animation here, it's just our perception, because there are too many vertical lines which will cause us this Moore effect. So we may feel dizzy if you stare this for too long. So the shimmering effect is going to be worse if we add some overlapping grids. So that's why many times when we create the line chart or other type of chart, we need to remove those kind of grid lines. They may actually cause the shimmering effect. So like this example. So we have 50 states of unemployment rates we want to compare. But this will obviously cause the shimmering, the Moore effect, because there are too many bars. Another similar effect is called Ferment Effect. It's also known as the Scintillating Grid. If you stare at all these squares, you're going to notice the dot, the gray dot in between. because when our eyes move around the grid, we get this kind of distracting effect. So this kind of a scintillating effect can be observed if you put this kind of a chart for comparison. You can easily notice this the gray dot in between all these squares. Another example is or principle is like the Scintillating principle. So if you stare at this image and see if you can see the white triangle that is on top of the 3 red circles. But actually there's no triangle there, but there are actually 3 pentagon shapes, but we can easily understand there's a white triangle in between. So in the same way, we can see the circle, the triangle, and the rectangle around them. But none of these are complete shapes. This is how our mind will work when we are presented with this type of information. So we tend to compare the image with our previous experience and interpret these objects, even though the objects are not complete. So what letter is this? Some of you may say it's H, others may say it's A. Because we do not have the actual context. If we add some context, vertically we can see it's H. Horizontally, we may argue it's A. So if we have the context, we can determine the meaning of the actual visual presentation. So another Gestalt principle is the proximity principle. So by inputting squares with different colors, we tend to group them together. So look at this image. Are there more blue squares, white squares, or red squares in this image? So if you just look at this and try to react immediately, you may there are more blue squares in this image, but actually we have the same number of blue squares as red and white squares. So objects that are near each other will appear to belong together. So we can adjust the spacing a little bit, which will create 4 squares, 4 rows, or 4 columns. By adding colors, we can show 4 columns, but alternating 2-row colors. So this is how we can use the different types of pre-attentive attributes to achieve different visual perception. So here's another example. If you stare at this middle black dot for 20 seconds, then you move immediately to the next slide. Let's see what will happen. So you may not immediately see the effect. If you do not, you can repeat this on your own. So if you repeat this, you're going to see actually the color is going to be transferred to the next slide. So even though the next slide shows you a black and white picture, but you can actually observe the colors being transferred from the previous slide. So this is how our brain is going to work. So our brain is going to process this information, and after a short period of time, the image is going to be embedded in our brain as a short memory. It's going to be transferred to the next slide for a very short amount of time. So here's another similar kind of an example. If you stare at this woman's nose, the red dot on her nose, for about 20 seconds, and then you try to move quickly to the next slide, see what will happen. So even though the next slide is actually blank, you're still going to see the woman appear on this slide. If you do not see it, you need to stare hard, very hard, you need to concentrate on this white dot for about 20 seconds, then move immediately to the next slide. You actually see a very pretty woman on the next slide. So if we put all this together, we can see that we live in a world that is rich with data. So data helps us look at the past, present, and make us predict future scenarios. So essentially, data is a powerful resource that we can use to help us to understand our world, to help us to make better choices. So we just need to discover how to how to do these things wisely to tell a good story with our data sets. Okay, so I'm going to stop here for a moment, and we will continue the discussion of the slides next week. So let me know if you have any questions. Feel free to drop me an email or just post the questions to Canvas. Okay.